Hey, physicist, F-Train here. This is the solutions to the two AP problems I assigned for homework today. All right, so number one, we've got a, by the way, it should take about 20 minutes to do this problem, just if you're keeping score at home. So 2 moles of a monatomic ideal gas are enclosed in a cylinder by a movable piston. The gas is taken through the thermodynamic cycle shown in the figure above. Okay, the piston has a cross-sectional area of 5 times 10 to the minus third meters squared. So it's going from A, and then you can see that it's going to undergo constant pressure, isobaric process from A to B, constant volume, isochoric process from B to C, and then from C back to A. That's not really any specific type of process. That's not isothermal. It's just a process. All right. So first, and then you're given the area, obviously, is 5 times 10 to the minus third. So you got this, you've got a thing here, you got a piston, and this is the area, and then this is piston, this is the gas in there. Okay. Lots of dots. Okay. Anyway, so calculate the force that the gas exerts on the piston. All right. So first thing you want to do is we know pressure is equal to force divided by area. And so there, of course, the force is just going to be equal to pressure times the area. Now, in state A, we know the pressure is 1 times 10 to the 5th pascals. So basically just 10 to the 5th newtons per meter squared, which is a pascal. And you multiply that by the area, which is, the area is 5 times 10 to the minus third meters squared. That's a 3 meters squared. And so you're going to end up with 5 times 10 to the 2, or just AKA 500 newtons. Okay, 500 newtons. Okay, so that is part A. Okay, oh, actually, but it says calculate the force and explain how the collisions of the gas atoms with the piston allow the gas to exert a force on the piston. By the way, this is one point right here. And the second point, you have to explain. And so basically you just want to say something like, as these molecules bounce off of the piston, okay, as they bounce back, they're going to exert a force on it. Or you could say that their momentum is going to change. And we know that force is the rate of change of momentum, or, they're going to accelerate because they're going to change direction. So that causes a force. So something like that, okay? And that'll give you another point for that, okay? I can read, it says here, the collisions of the gas molecules with a container cause a change in the momentum of the gas atoms, which means forces are exerted between the atoms and the piston. Each gas molecule colliding with a wall experiences a force from the wall that changes the molecule's velocity or momentum, okay? So that's the official answer that they give, all right? Basically, the molecules are bouncing into there, causing a force, okay? Number 2, calculate, this is A, part 2, calculate the temperature of the gas in state B. So you want to calculate the temperature of the gas in state B, and then indicate the macroscopic property of the gas that is characterized by the temperature. Well, all right, so to start out with, what we can do is we can say that at state B, we know the pressure is 1 times 10 to the 5th, and we know the volume is 0.1 meters cubed, right? And so to find the temperature, we can use PV equals nRT. And the reason we could do that is because we know N. It tells us that 2 moles are, 2 moles of gas are present, okay? So the temperature is just going to be PV over NR. All right, and we've got our P is 10 to the 5th. Our V is 0.1. Okay. Our N is 2. And our R is 8.31. And so that gives us a temperature of 602 Kelvin. Okay. All right. So the second part, so that's 1 point there. So the second part, though, is indicate the microscopic properties. So as you recall, temperature is a measure of the kinetic energy. So, you know, kinetic energy is 3/2 kT. So temperature is a measure of the kinetic energy of the molecules, okay? Or you could say the average velocity of the molecules in the gas, all right? So something like that. It's for the extra point, all right? All right, let me just pause for a second. Okay, so I just made a copy of the diagram so we can see it for this part here. Okay, so we've got, it's saying, predict qualitatively how the internal energy of the gas changes as it's taken from state A to B. So as it goes from A to B, the internal energy. All right, well, we know that internal energy is equal to 3/2 nRT, which we know that PV is nRT, so internal energy is also equal to 3/2 P times V, okay? And qualitatively, that means they don't need you to know like how much it's increasing. But we definitely know that if the pressure is staying constant, which it is from A to B, and if so the pressure is staying constant, but the volume is increasing. And in fact, the volume is going from 0.4 to 0.1. So it's like 0.04 to 0.1. So it's increasing by a factor of like 2.5 times. That means the internal energy will also increase by that same factor. Okay, so basically the internal energy will increase. All right, and so and then so that's 1 point for saying increase, 1 point for saying it increases, and then 1 point for justifying. So, you know, by, like I said, saying that, you know, U is nRT, U 3/2 nRT, and so also 3/2 PV. So if PV increases, then the internal energy increases. So anyway, that's the second point for justifying. Okay. Calculate the energy added to the gas by heating as it is taken from state A to C along the path A, B, C. Okay. So the energy added to the gas, now we know that energy added is basically the same thing as saying heat, right? Because heat is the energy that you're adding to a gas, okay? By heating, it says heating, so it's kind of heat. All right, so as we go from A to B to C, we want to figure out how much heat. So we're going to use our delta U equals Q plus W. So really what we're trying to figure out here is what Q is. So we know that Q is going to be equal to delta U minus W, okay? So that's what we're trying to figure out. We're trying to figure out, oops, sorry about that. Okay, so so how do we find delta U? Well, oops, F train. All right, so delta U is going to be 3 halves. Well, actually, let me think of it this way. Okay, U is 3 halves nRT, but PV equals nRT. So U is actually 3 halves times PV, okay? So let's do U at C. U at C is gonna be 3 halves times pressure at C, which is 0.5 times 10 to the 4th, 0.5 times, I'm sorry, 10 to the 5th, okay, times the volume, which is 0.1. So we get, so that's 0.5 times 10 to the 4th, which is 5 times 10 to the 3rd, 5 times 10 to the 3rd, which is 5,000, times 3 halves is 7,500. So that's U at C. Okay. U at A is going to be 3 halves times 1 times 10 to the 5th, right? That's the pressure at A, 10 to the 5th, times 0.04, 0.04. Okay, and so let's see, that's going to be 1.5 times 10 to the 5th divided by 100 is going to be, I think that's all going to be 6,000. Yeah, 6,000. Okay. And so what is the change? The change is going to be 1,500, right? So it's going to change by 1,500. Final minus initial, UC minus UA is going to be 7,500 minus 600. So it's going to be delta U is going to be 1,500. Okay, now I am totally running out of space. So I'm going to have to do something about that. But I also want to figure out what W is, okay? So again, we're going from A to C. Now, we know that from B to C, there's no W, right? So no work, okay? So I can just figure out the work from A to B because there is no work from B to C. So that's just going to be equal to negative P delta V, okay? Negative, now the pressure is 10 to the 5th. All right, the delta V is going from 0.4 to 0.1, so 0.04 to 0.1, so that's 0.06, 0.006. Okay, and so 0.06 times 10 to the 5th is, this is 6 times 10 to the minus 2, times 10 to the 5th, so it's going to be 6 times 10 to the 3rd, so that's going to be 6,000, negative 6,000, because it's expanding, and negative 6,000. So it's going to be negative of a negative 6,000, right? Because it's minus. So minus negative 6,000. So it's heat added. So this is a good sign because 1,500 minus negative 6,000 is going to give me positive 7,500 And that's going to be the Q, the heat added here, okay? All right, and let me just check the answer. I hope I'm right. If not, yes, I'm right. Okay. All right, so that is that part. So let me just pause again and okay, and then lastly, it asks us what is the total change, the change in the total kinetic energy of the gas as it goes from state C to A. So from C to A. Okay. Well, so what we could do here, all right, we already know the change. So basically, you know, in a gas like this, right, kinetic energy is, so internal energy is basically kinetic energy plus potential energy. Okay. Well, we don't call it, I guess let's call it PE for his, okay. But in an ideal gas, there is no potential energy. So basically the kinetic energy is the same as the internal energy, okay? Now, I remember in, oh gosh, what was that? Let's see, let me look back. In part B, part 2, we found the change in internal energy from A to C, okay? So from A to C, we found out the change in internal energy was 1,500 joules. It increased by 1,500 joules, okay? So that means that UC minus UA is 1,500. Well, if UC minus UA is 1,500, then what is UA minus UC, final minus initial, if we're going from C to A? Well, delta U. So in other words, delta U from A to C was 1,500. So that means delta U from C to A is just going to be minus 1,500, okay? Okay, and since we said that U and K are basically the same, that means that's also going to be equal to delta K from C to A. So it's just negative 1,500, okay? And determine just means, I think that means it'd just be 1 point. Yeah, you don't have to explain anything. You just give them the answer, all right? All right, well, I think that's about it for that question. All right, so let's move along to the other question. All right, so for this next one here, we have an experiment is performed to determine the number of moles N of an ideal gas in the cylinder shown above. Cylinder is fitted with a movable frictionless piston of area A. The piston is in equilibrium and is supported by the pressure of the gas. The gas is heated while its pressure P remains constant. Okay, measurements are made of the temperature of the gas and the height of the bottom of the piston above the base of the cylinder and are recorded in the table below. Assume that the thermal expansion of the apparatus can be ignored. Write a relationship between the quantities T and H in terms of the given quantities and fundamental constants that will allow you to determine N. Okay. So what we want to do, I guess, is say we're going to use our basic equation that is that has N in it, right? That has T. And the given quantities, which were pressure P, so P V equals N R T, okay? All right, now we don't have V, we only have H, but we have A. So we know that V is equal to the area times the height. So we got P area times the height, because area times height is going to be volume, is equal to nRT. And so what is the relationship between T and H? Well, I guess you could say that H over T equals NR over PA. It seems like as good a relationship as any. Okay, so now I plotted up the temperature on the x-axis, okay? And I plotted the H on the y-axis. So now if I get the slope, okay, so let me see if I can figure out how to do this, make a best fit line-ish. Okay, so if I can find the slope of that line, okay, so the slope is going to be H over T. Once I find the slope, H over T, I know R, I think I know P. Well, they're going to give me P, 1 atmosphere, and they're going to give me A. So then I can figure out N. That's the goal here, okay? So plot the data so you'll be able to determine N. Okay. So yeah, so I'll figure out the slope. So my slope is going to be, let's see, my slopage is, my slope is going to be my rise. So I'm going from like 1.1 to, let's say, 1.45. Let me see if I can find two better ones. All right, let's use 1.1 to 1.45. So my rise is going to be 1.45 minus 1.1, 0.35. 35 divided by my run, which I'm going from 300 to about 410, I'll say 300 to 410. So that's going to be 110. Okay, so that's my slope. All right, and then down here, they're gonna ask me to actually figure out what N is. Okay, so I'm gonna do it up here because I have a little more room. So my N is gonna be my slope. Okay, which is, so N is going to be slope, which is H over T. Okay, divided by R, multiplied by P times A. Okay, I think that's right. All right, well, let's see. So I've got H over T is 0.35 over 110. Okay. My pressure is 1 atmosphere, but I need to convert that into Pascal. So I'm just going to call that 10 to the 5th Pascals, because I know that 1 atmosphere is like 1.01 times 10 to the 5th Pascal. So let's round that up a little bit. My area is 0.027. 0.027 is my area. Okay, H over T times P times A, and divide that by the constant, which is 8 point something. Let me see, what is that? 8 point. Hold on, I gotta look it up. Hold on, the old gas constant. 8.3. 8.3145, something like that. Okay. All right, time to get out the old calculator. So we got 0.35. Actually, I'll pause it so you don't have to wait for me to calculate. All right, so I get about 1 n is equal to 1.003 moles. Okay, so 1.03. Now, I looked up the answer that they get 1.1. You know, anytime you're doing something like this, you're finding a best fit line, you're going to have a little bit of error. So I'm going to say my 1.03 is close enough to 1.1 that I would get a point. So, or however many points it is. All right, so that's it. So you figure out the equation, H in terms of T. I didn't even do that on purpose, but it came out well because H over T is the slope. Okay, and the slope is going to be equal to NR over PA. Okay, and so therefore I can find N is just the slope times P over R, plug everything in, you get the right answer. All right, anyway, I hope you had fun with those, and I will see you guys very, very soon.